Hey guys, Mr. Marone here. Welcome back. We are continuing our discussion on similarity in right triangles today with our day 2 notes for G.SRT.B.5. And we're going to look at what are called special right triangles today. So we've discussed right triangles up to this point, and we haven't had anything shortcut-wise to be able to do. Now we're going to be able to have some shortcuts to work with that make life a little bit easier for us. So the first one we're going to look at is the 45-45-90 right triangle. And that's created when I take a square and I draw a diagonal in. So if I draw a diagonal across my figure here, it creates two right isosceles triangles. So draw a diagonal, and that creates two right isosceles triangles. And it creates, in this figure, a couple things for us. We know we have 45-degree angles here from our previous notes on quadrilaterals. And what else we have here are two congruent sides, so they're an isosceles triangle, as we've stated. And we end up with two different labels that we refer to. The longest side in any right triangle we refer to as our hypotenuse, and we shorten that to HYP. And then we have what are called two legs, the parts that create the right triangle, create the right angle more specifically. And in this case, both of our legs are exactly the same. And that creates some shortcuts for us, as we're going to see in a second. So let's take a look at a couple, and let's just solve these right triangles in the best way we know how, which is Pythagorean theorem right now. Okay, so for my first one here, it's going to be 10 squared plus 10 squared equals x squared. And I end up with 100 plus 100 equals x squared. So I've got 200 equals x squared. And when I take the square root of that, square root 200 can be broken into square root of 100 and square root of 2. So I end up with 10 square root 2 for x. If I do the same process for my second one and my third one, we're going to end up with a similar result. I've got 36, that's a terrible 3, sorry guys, 36 plus 36 equals x squared, 72 equals x squared, and when I take the square root, I end up with square root 36, square root 2, 6 square root 2 for x in my second one. And if we finish this off, 2 squared plus 2 squared equals x squared. And I get, let me just move this over, I end up with 4 plus 4 equals x squared, 8 equals x squared, and the square root of 8 we know is 2 square root 2. So if you notice, this creates a little bit of a relationship here. And it tells us that we already knew our legs are equal. Okay? They're always going to be the same because it's an isosceles triangle. But what this does for us, our second thing, is that our hypotenuse is going to be equal to square root 2 times the measure of my leg. You notice in all three of these, the answer was just the leg measure times the square root of 2. And that allows us to solve any of these problems using this rule. It's just one rule, and it's a really quick shortcut. So we've got 6 problems here in our examples that I want you guys to take a look at. Okay? In each one, they've given us the hypotenuse. And we have to divide by 2 to get our leg, because we said that our hypotenuse is equal to square root 2 times my leg. So if I'm given the hypotenuse to solve for the leg or get the leg on its own, I have to divide by the square root of 2. In my first one, 8 square root 2 divided by square root 2, those are going to cancel out, and I've got 8, which is my answer for x. Okay? Same thing's going to happen in the second one. 3 square root 2 divided by square root of 2, I end up with 3, which equals x. And in my third one, it kind of works out for us. I've got square root of 8 divided by square root of 2. Think of that as being written just like this. Square root of 8 over 2, which is square root of 4, which is just 2. So x equals 2 in that case. When we get down to the bottom ones is when we start to have to really think about it. Okay, so for my fourth problem here, 5 square root 6 divided by square root 2 gives me 5, and then 6 divided by 2 is 3. So 5 square root 3 for x. Reminding that x is the same for both ones. When we get to 5 and 6, this is where it gets a little trickier. We're going to have to use something called rationalizing our denominator. So if I divide 8 by square root of 2, we can't divide by a radical. We can simplify with a radical on the top, but we can't divide by a radical. What we have to do is a process called rationalizing the denominator. And I'm going to refer to this as, my joke is that it's math black magic. We're doing something mathematical, but at the same time it looks very different. So I'm going to multiply this by 1, which keeps the fraction exactly the same if we're multiplying by 1. In this case, I'm going to multiply by square root of 2 over square root of 2, which is just 1. Any number divided by itself is 1. But what it does is it allows me to multiply across, and I end up with 8 square root 2 on the top, and I end up with the square root of 4 on the bottom, which simplifies to just 2. So I've got 8 square root 2 over 2. 8 divided by 2 is 4, so I end up with 4 square root 2 for x. So it's a way to eliminate that radical on the bottom. If we multiply any fraction with a radical denominator by the value underneath the radical, it will clear out that radical and allow us to actually move forward. So if we take a look at number 6 here, the last one, 6 divided by square root of 2, we're going to once again rationalize. Multiply top and bottom by square root of 2. And I end up with 6 square root 2 over 2, which gives me 3 square root 2, which is what x's value is going to be there. Okay, so this rationalizing the denominator trick is a really useful one to have. And I hope you guys find it helpful as you move through. So you guys have some practice problems tonight. It's your second to last homework in this unit leading up to our big test to finish it off. And bring any questions you may have into class tomorrow with you.